So the next pattern to be covered is the interpreter pattern. Let's take one example. I have a Boolean expression, which is this line, which is z and x or y and not of x. And this expression has to be evaluated for the following values of y. X takes a value of true, y takes a value of false, and z takes a value of true. So this is simple, right? All we got to do is replace the values of x, y, and z in this expression and then find it out. So in this case, x is true, z is true, so true and true is true. And that is odd with something, but true odd with anything is true. So this would evaluate to true. Now this is how we would do it manually. Now suppose we have to write a program which takes an expression like this and evaluates it. Then how are we going to do it? So that is one question. And before we get into how do we solve that problem, there is one thing which we need to understand is that expressions like this is actually just an instance of a grammar. It's a sentence of a grammar. So the previous Boolean expression which I showed is an output of a grammar which has 1, 2, 3, 4, 5 rules. So this grammar has 5 rules. The first rule is, let's read from the bottom, is a variable expression can have any of the alphabets A to Z. So A, it can be A, or it can be a B, or it can be X, Y, Z, any one of them, any of the alphabets. A variable expression is a Boolean expression. Okay. And two Boolean expressions can be combined to form an AND expression. Two Boolean expressions can be OR to form an OR expression. And a Boolean expression can have a negation which forms a NOT expression. And a Boolean expression can be a variable expression or OR expression, AND expression, NOT expression, or Boolean expression in this also can be there in terms of in brackets basically. Okay. So this is a grammar, and the expression which we saw in the previous slide is actually one sentence produced by this grammar. Okay. Any question on this grammar? No? Okay. So my problem is to design a unit like this or a module like this which takes two inputs. These are the two inputs. The first input is a regular expression, which is the problem statement, which is z and x or y and not of x. So the first input to this module is this regular expression. And the second input to this module is the values of variables x, y, and z, which happens to be true, false, and true in this case. And the output of this module is the value of this regular expression, which is going to be true in this case. So we would solve this problem in 3 steps. And let's just blindly follow the 3 steps. The first step is to create the class hierarchy and implement the methods. Now when I say create the class hierarchy is shown in this particular picture. And this class hierarchy is going to have a class for each of the rules of the grammar. Now my grammar had a rule called variable expression. So I would create one class called variable expression. And this variable expression class is going to contain a char star underscore name, which is the name of the variable. So this is my class. And this class is derived from an abstract class. Let's call that class as base class as a Boolean expression. So the base class just tells you that it has a interface method called evaluate. Okay. Now how many more rules we had in the grammar? Okay, let's try to list out the rules without going back. How many more rules? How many other rules did we have in the grammar? So we had one rule which was variable exp. Which were the other rules? I had an AND. The AND rule was what? So for this rule, I have a class which is AND exp. So we are actually right now following the pattern blindly. So the moment I see a rule in the grammar, I would create a class for that particular rule. For this AND expression, I have AND expression class over here. And this AND expression works on two Boolean expressions. So this class is going to have two Boolean expression pointers, exp1 and exp2. Now these are pointer to the base class object. Okay, so since these are pointer to the base class object, it can actually contain pointer to any of these three things, right? Right? Because a base class pointer can store an object of the derived object. So a Boolean expression, a AND expression works on two Boolean expression. So these two become the data members of the AND expression class. And evaluate is a method which would evaluate these two Boolean expressions. Which was the other rule in the grammar? OR. I had a OR exp. So for OR exp, I again had a B exp and then OR of B exp. So I would blindly again go and create a class by the name OR expression for this particular grammar. So there is a OR exp which is again derived from Boolean expression. And this OR exp also takes, it shows pointer to two Boolean expression object. Okay, and this also has an evaluate. So this evaluate is responsible for evaluating these two expressions. And then we had a NOT expression, right? So this was NOT of exp. So this is my NOT exp class, and this has only one data member because this works on only one Boolean expression. It calculates the negation of that particular Boolean expression. Okay, so these are the, for every rule over here, we had one classes, right, and the base class. So this was the first step in solving that problem. Now this is not complete because we listed down the methods and the data members and the class hierarchy over here, but we still have to find out what do we do in evaluate. So evaluate of the base class is 0 because this is my base class, so abstract class. So there won't be any objects of Boolean expression. So this is 0. Now let's look at evaluate of variable exp. What is that going to do? Okay, so by the way, before we get into evaluate, let's understand what is there in this context object. So we also have a context object or context class. The context class implements a method called lookup, which all it does is it takes a variable name and returns the value of that. So this has a method lookup. If you pass on the name x over here, or you can also pass that variable exp object itself because that contains the name. So let's overload this context class. So if you pass on the name of a variable over here, it stores the value of those variables. So if you call the lookup method of this context class with a value of x, with a parameter x, it would tell me that x has a value of true because we have to evaluate the expression for x true, y false, and z true, something like this, right? So when I create my client object, I would create a context object and I would do c.assign x true. So this also has to happen assign. Okay, we would see this part in more detail. So this context class, all it does is it keeps a mapping between the name of the variable and the value of that variable. Okay. So the evaluate of this variable exp, what is that going to do? It would get me the value of the variable, which is represented by this variable exp object. Okay. So that's the last one. The evaluate of the variable exp, it takes a context class and it does a c.lookup. The name is from the variable exp object and just returns the value of that variable. The evaluate of the and exp, this also takes a context class, and all it does is exp1 evaluate c1 and exp2 evaluate c. Because we know that this class is for AND expression. So if there are two Boolean expressions which we have, it has to do a AND of those two Boolean expressions and return the value of that. Now the evaluate of the OR exp, it calls evaluate of the exp1, evaluate of exp2 and does a OR on that. So simple. Whatever the operation is, it does an operation, that particular operation on the Boolean expression it has and returns the value of that. Evaluate of not exp, all it does is calls the evaluate of exp and does a negation of that and returns the value of that. So this completes the step 1, which is create the class hierarchy and implement the methods of that. So there is one more thing which I did not talk about is, we talked about this relation. So this means that AND exp is derived from Boolean exp, not exp is derived from Boolean exp, and similarly these two classes. But what about this relation? So this shows an aggregation, which means that AND exp is an aggregate class, and it can contain multiple objects of Boolean expression. So as you can see over here, this indicates this is an aggregation. So it means one or more objects of Boolean expression, either directly or as a pointer. So in this case, it has two pointers for Boolean exp1 and exp2. Similarly, not exp also has this aggregation relationship with Boolean exp, and this also has an aggregation relationship. Okay. So we said that there are 3 steps to solving this problem. So we are done with the step number 1, which is create the class hierarchy and implement the methods. So how we created the class hierarchy was, we just took the grammar. For each grammar, we created one class, identified what data attributes it should have, and implemented the evaluate method of the class. Now step 2 is, the client code should create the parse tree or the abstract parse tree. And the third step is to invoke the evaluate method of the root node. So let's go to step number 2. So there are 3 variables in my example. My expression was, let me write down the expression over here. There are 3 variables in my expression. One is x, the other is y, and the third is z. For each of these variable or variable exp, I create an object called variable exp. And the constructor of this takes this character x and stores the name x in underscore name. Again, for y variable, I create a variable exp object. Because each of the variables, they are going to be represented by one variable exp object. And then the last line is this complicated stuff, which means I would create a AND expression object and this AND expression object takes two pointers. One is Z and X. So note these are small z and small x, not capital X and capital Y. My expressions are capital X, capital Z and capital Y. And these small x, y, z, these are pointers to the variable exp object. I create an AND exp object which takes two variable exp pointers, z and x. I create a not exp object which takes a pointer z, which is variable exp, and then one more AND exp which takes this y and the new of this not exp object, and this OR expression object takes these two as a parameter. Okay. So what happens is the last line, when the last line gets executed, you have a tree like this created. See, in the first three lines, what we did was, in the first four lines, in the first three lines, we created a variable exp object, and then a variable exp for y, and a variable exp for z. That was the first step. Now, in this expression, when this expression gets evaluated, and assuming that the parameters are evaluated from left to right, or if it is right to left, then let's take it this way. Then the next thing to be executed would be a not exp object. So the not exp object is created over here, and this not exp object takes a pointer to variable exp, and this had a Boolean expression star exp, so that is made to point to this variable exp. So this part of the tree is completed when this was executed. Now the next thing to be executed would be this new of AND exp, and this new of AND exp would create a AND exp object, and it could take two pointers. One is y, which is variable exp for y, and this not exp object. So when that gets executed, this part of the tree is getting created. This one or this one? This one? Yeah, this one. So this was created because we are evaluating the expression from right to left. A new of AND exp was done, and two pointers were passed. One was pointer to not exp, and the other was pointer to variable exp. And then we did a AND exp, new of a AND exp. Oh, that's what we did. And then, so after this is executed, this new of AND exp would be invoked. Now this takes as z and x. So which part of the tree gets created? Left one, right? This AND exp got created, it took two pointers, variable exp and variable exp for z and x. Now the final thing was this new of OR exp, and it took two pointers. So then which part of the tree got created? Only one is left, which is this one, right? So this would get created. So this is called as the abstract syntax tree. For every expression or every sentence which can be generated by the grammar which I showed, we can have, or we will have, one abstract syntax tree, and this tree represents a grammar like this. Okay? So coming back to this picture, I took one regular expression, and by the way, this grammar interpreter is for a specific grammar. So this grammar interpreter, it cannot take any grammar and then generate a code for that or work for that. So the grammar interpreter, the step one which we did was, for a specific grammar, we created those classes, implemented those hierarchies, and implemented the methods. And the second step was to take a regular expression and create an abstract syntax tree for that regular expression, the picture which we saw. Now the third step is invoke the evaluate method of the root node. So the step tree would involve these things. I would create a context object called C1. I would do C1.assign x as a value of false, C1.assign y as a value of true, and C1.assign z as a value of false. And then for the expression, for the abstract syntax tree which got created, I would call the evaluate method with this should be C1 actually, with passing this the C1 object to this evaluate. Now the moment I call this evaluate, so the evaluate of which class is going to be called? The topmost, right? And this class or exp has two members, exp1 and exp2, both of which are Boolean expression. And all it does is calls the evaluate of both the Boolean expression and does a OR of the output. Which is this piece of code. This OR exp object at exp1 and exp2, it calls the evaluate of exp1 and evaluate of exp2 and does a OR of that. So all we did in this case was we ended up calling the evaluate of and exp and this and exp and this and exp. Okay, and the evaluate of and exp would do the same thing. It is going to call evaluate of variable exp and variable exp and do the AND of the output of that evaluate. Correct? Which is this one. It is going to call evaluate of exp1 and exp2 and do an AND of that. Now the exp1 and exp2 in this case represent which object type? Variable exp. So this is how it traverses through the entire tree. And finally, when all these methods return, you would get a value of true printer. You can just try it out and see. So there are a couple of loose ends in this explanation which we would cover now. First of all, what is a grammar? What is a terminal symbol or non-terminal symbol? The second question is, how do I create the abstract syntax tree? Because the way we created the abstract syntax tree seems to be very basic. It would work only for simple expressions like we had. What is a general algorithm to create an abstract syntax tree? Because once I have the abstract syntax tree, I can very much call the evaluate method of the root node and then evaluate my expression. So how do I create the abstract syntax tree? Third question is, this pattern seems to be applicable more for compiler, so why should we bother about it? And the fourth question is, which are the other examples in which this pattern can be used or is applicable? The first question, what is a grammar? What is terminal symbol and non-terminal symbol? So we briefly touched upon this. So a grammar has a rules like that, and we have read this in our textbook and forgotten. So, but the rules look something like that, which I showed in slide number 3. It would have those rules, and a grammar has a language, a set of sentences which are generated. So the grammar which I showed for the Boolean expression, any Boolean expression which involves variables with and, or, and these parentheses are generated by that grammar. But if I have a expression like so my where and your where, will this be a valid sentence from the grammar which I showed? If I write a Boolean expression like this, my where and your where, this will not be. The reason is the entities can only be one variable, which is alphabets A to Z. It does not take a string like this. So if I want this also to be a valid grammar, this rule has to be modified. And what we can do is, we can do a or with A, B, Z, and then put a star over there. So if I change that variable exp this would continue to be what it is right now, and I would add this part. So in this case, this would be considered as a valid Boolean expression generated by this grammar, but not the current one. The second question is, how do I create the abstract syntax tree? The way we created the abstract syntax tree was very basic and is impractical. So the answer here is, the interpreter pattern does not explain how to create an abstract syntax tree. That is something which is out of the scope. It doesn't address parsing. It does not address, the interpreter pattern does not address the parsing of the Boolean expression. The abstract syntax tree can be created by a table-driven parser or by a handcrafted parser, like generally you have this recursive descent parser. So these can be used to create an abstract syntax tree like the one which we saw. The third question was, the pattern seems to be more applicable for compiler and stuff like that, so why should we bother? Now, I have seen applications like DB API. Most of these telecom applications generally has a man-machine interface, MMI. You call it MMI. In MM1 case, it used to be called as DB API. In MM2, it got renamed to MMAdmin. In EBDO, also we have a bunch of MMI commands. These MMI commands, they work on the PAN. And it displays some data structures, it prints some information and stuff like that. So at least in case of DB API, I do see one grammar which is defined for the commands which can be passed on to DB API. So on the DB API, I can give a command like status and then redirect that output to a file. Or I can give some other dump or something, or we used to have that mdvg for changing the debug level of a process. So all these commands are represented by a grammar. And in fact, DB API makes use of lex and yak to parse. It does not make use of the interpreter pattern. But all I wanted to say was, interpreter pattern can be used in such cases. So in case of DB API, it was simple. They had a two file, analyzer.lex and parser.while. The first is the input to the lex, and the second is the input to the yak. And once it recognizes a command that, oh, this is a status command, and then the output of this has to be redirected to this file. Once the yak part of the DB API recognizes that, it runs this and redirects the output of this to this file. But there are applications, and it can be used in our cases also, in telecom application. And of course, many of us have implemented a Unix shell in our college projects. So a shell, like a K shell or a Bourne shell, can take commands like ls or move or whatever, move or date or something. And then you can pipe out the output of that command to some other command. And so the language, the set of valid commands can be represented by a grammar. Because see, you have to make sure that the user does not type an incorrect command. And if you try to manually do it, instead of trying to represent that as a grammar, the code would become very complicated, and it may not be possible to handle all cases very efficiently. Because you can have 5 files and then 2 redirections and 1 T in a command, right? So there are cases where we would need a grammar, and there is a possibility of using a interpreter pattern in that case. Okay, so one more example is that of a regular expression. Given a regular expression and an input string, okay, I did not type it completely, but all it says is, given a regular expression and an input string, find out if this input string matches this regular expression. So this is another example, which I have it in the slides, but we may not cover because due to lack of time, but I do have that example also in the presentation. So this is one case in which again we can make use of interpreter pattern. So let's talk about some theoretical stuff about the interpreter pattern. So the intent of this pattern is, given a language, so language here is grammar, given a language, define a representation for its grammar along with an interpreter that uses a representation to interpret the sentences. The intent here is to represent the sentence, interpret the sentence. So either you interpret the sentence, or in case of Boolean expression, we were actually trying to evaluate the value of that Boolean expression. we can have a different variant of that example in which we just tell if this Boolean expression follows the correct syntax or not. That also could be possible. So it's not that you always try to evaluate the expression. This part, the interpret the sentence, can be as simple as find out if this particular sentence has the correct syntax, or in case of Boolean expression, evaluate that. This is the structure of the interpreter pattern. Let's try to see the components of that. So I have an abstract expression class. Now this maps to which class in my Boolean expression hierarchy? Boolean expression. And this is the abstract class. So as you saw, the evaluate method in the Boolean expression was actually a pure virtual method. So this only defines the interface. Nobody is going to create an object of this particular class. And from this class, we have two categories of classes which are derived. I have a class called terminal expression, which is derived from abstract expression. This terminal expression maps to which class in the Boolean expression hierarchy? Variable exp. Because my grammar has two kinds of symbol. One is a terminal symbol and a non-terminal symbol. A terminal symbol, the official definition of a terminal symbol is the one which cannot be replaced. Okay. So if you have a variable a, b, c, d, or any of those variables, they cannot be further replaced to form a bigger sentences, or rather combined to form a bigger sentence. But a AND expression, they are non-terminal symbols because they can be expanded by the rules of the grammar to make the expression bigger and bigger. So for non-terminal expression, I would have one more class which is going to be called as non-terminal expression, and this is again going to be derived from abstract expression. And all these two derived classes are going to have an interpret method. And this takes a context class. The context class in our case, all it had was x has a value of true, y has a value of false, z has a value of true. So in order for these classes to run the interpret, it would need the context, the current context. So this is basically about the inheritance, the derivation over here. Now what is this relation? This is the aggregation. So this class, the non-terminal expression, is an aggregate class to the, and we saw like examples in case of AND exp and OR exp. This class had pointers to a Boolean expression, so they are actually aggregate classes. And then you have a client class. The client class also interacts with the context class, and client would invoke the interpret. Now, whose responsibility is to create the abstract syntax tree? Which class has to create the abstract syntax tree in this picture? The client has to create the abstract syntax tree, and the client has to invoke the interpret method of the root node. So participants, we talked about it. Abstract expression. To declare an abstract interpret operation that is common to all nodes in the abstract syntax tree. Terminal expression. Variable exp was the terminal expression. This implements an interpret operation associated with terminal symbols in the grammar. An instance is required for every terminal symbol in a sentence. Like x, y, z, all three of them, they had an object of type variable exp. Non-terminal expressions. Examples of non-terminal expressions are AND exp and OR exp. One such class is required for every rule. So in my grammar, the rules are of the form r::, r1, r2, rn. This is my grammar. So, and this maintains instance variable of type abstract expression for each of the symbols r1 through rn, and implements an interpret operation for non-terminal symbols in the grammar. And interpret typically calls itself recursively only on the variables representing r1 through rn. So we have seen how it was actually done for the Boolean expression itself. Context contains information that's global to the interpreter, and client builds or is given an abstract syntax tree representing a particular sentence in the language that the grammar defines. The abstract syntax tree is assembled from instances of non-terminal expression and terminal expression class, and the client invokes the interpret operation. So question, how is the interpreter pattern different from composite? composite we did cover. Let's try to draw the structure of the composite pattern. So if it is files and directories, for the Unix file system, we had two entities. One was files, the other was directories. So for this files and directories, if I have to create a class diagram, what all should be part of that? Sorry?
File system element.
Okay, file system element, which is a base class, right? And then, how about, so file and directory, there are going to be two classes, one representing file, other representing a directory. So, this file has to be derived from this FSL, right? Correct? Because file is a FSL. And then we had a directory. So directory is also a file system element. So I would have a class for the directory. And the directory is an aggregate class. Because the directory can contain files and directories also. So this is an aggregate class containing files. So this eventually can have pointers to files as well as directories. Because it's an aggregate to itself, right? Now this structure is same as this structure, right? So how is a composite pattern different from an interpreter pattern? The composite pattern is a more generalized form, but the interpreter pattern should be reserved for those cases in which you want to think of the class hierarchy as defining a language. It's the same. There is no difference. But a composite pattern is a more generalized, and the interpreter pattern is a little specific to the language. Use interpreter pattern when the grammar is simple Again, this sentence is not complete. So use interpreter pattern when the grammar is simple. For complex grammar, it becomes difficult to manage things, and you would want to make use of something more complicated like Lexan Yak, which is very easy to use. So coming back to what is the distinction between interpreter and composite. So there is not much of a distinction. Composite pattern is a generalized form of the interpreter pattern. And all the interpreter pattern does is, it just gives you an idea in your mind that whenever you have a grammar, feel free to make use of the composite pattern for that. And it just gives you a thought in your mind that for each of the grammar, you can create a class which can derive from the abstract expression. So all it does. Otherwise, it has the same structure as that of composite pattern. So this is the next example of interpreting sentences. We will not go through it. But again, as the class diagram indicates, a regular expression, this is the grammar for a regular expression. So this is my regular expression. This is my regular expression, right? A word called identifier called raining, and with dogs or cats, stuff. So a regular expression can represent multiple sentences, right? If I have raining, dogs, this also matches my regular expression, correct? If I have raining, dogs, cats, this also matches. Raining, cats, this also matches. So this regular expression matches all these sentences. Now this regular expression has a grammar, and the grammar is these 5 rules. So as you can see, this part has ABC star, and then there are basically 3 operations in the regular expression. One is a and, the second one is a or, and the third one is a star. Like we had raining or. So this rule specifies that, that's the alteration. And then cat and dogs. So cat, this is the and expression, which is a sequence. And then repetition, which is a star. And this is the final rule which clubs everything. So here again you can create a class diagram like this, which is just following what has been recommended in the textbook, that for each of the grammar rules, create one derived class. So for literal expression, I have one class. For sequence expression, I have one class. For alteration, for repetition also, I have one class. These three derived from the regular expression class, and they are aggregates. And then define an interpret for each of these classes. The interpret of this class would call interpret of the two expressions it had, and it would do an AND of them. So that was basically example number 2 at a very high level. Of course, we don't intend to go through it. So that's it. I mean, we have come to an end of this pattern. Any questions? Okay, thank you. And next week is the last session, and there are 3 presentations. One is Sharvari, second is Sachin, and third is me. Okay, thank you.